5.1, uniform circular motion. So this is basically what happens when you go around a circle. Um, so the definition, as I just said, of uniform circular motion is the motion of an object traveling at a constant uniform speed on a circular path. Sorry, this is the intermediate value theorem for calculus. And let's say there's like a race car right here. I mean, it's not like a perfect sphere, so it's kind of hard to draw because the racetrack is not really going to be inclined here. But let's just say that this is the racetrack right here. All it means is that it's going around this entire circle at a constant speed. So the speed vector here is the same as the speed vector here. Now the reason why I don't want to say velocity vector is because velocity has a direction. And we'll learn about this in the next one. And the instantaneous velocity is, remember, they're just the slope of the tangent line or the derivative formula. So it will be right here. So this is where the car is going. And then when the car is right here, it's going this way. And then when the car is going here, it's going this way. So basically the slope of the tangent line or whatever makes a 90-degree angle here. But in simple terms, uniform circular motion is when something is traveling around another thing in a circular path at a constant speed. And I say speed because speed has no direction. And the speed here is the same as the speed here. But the velocity here and the velocity here is not necessarily the same. Because although they are of the same magnitude, they are not of the same direction. This looks like it would be like 95 degrees, while here it looks like a 180 degree direction. So uniform circular motion, you can read it here. Uniform circular motion is the motion of an object traveling at a constant uniform speed on a circular path. Remember that we don't necessarily say velocity, since that vector changes direction every second in uniform circular motion, and that's why there technically is an acceleration vector, but I don't really want to get into that right now because that's the next lesson. And that one has a pretty challenging proof. I mean, this is like the first physics thing that actually challenged my brain. Because it has to do with ratio of triangles and whatnot. So if a race car is right here and it's going this way, same magnitude as right here, because remember they have to be the same speed, but they're different directions, which is why we say speed and not velocity typically. So that's the definition of uniform circular motion. This derivation is actually quite simple. You can read it if you like. Velocity equals 2 pi r over time. Takes to do 1 lap. How is it derived? Since velocity is constant around the circle, or speed, which it doesn't really matter here, I guess, because, I mean, I don't know. It just doesn't really. Because in a circular path, we'll always return to the same starting point. Well, if you land at the same starting point. So remember that a circle's circumference is 2 pi r. So that means this length of this entire circle right here, or the path, we would say, in physics terms, is 2 pi r. So 2 pi r divided by the time it takes, actually I probably should put t, gives us the units of meters per second, which is, guess what, velocity, because that 2 pi r gives us the circumference in meters or in whatever unit you're using, and the t will give us the time, which is derivation formula. But to even extrapolate that further, you can use English terms, and it would be vt equals 2 pi r, because velocity times time equals displacement. So basically we're checking the time it takes to make one full rotation, dividing it by the time on both sides, which is a derivation here. And 2 pi r, or the circumference divided by how long it takes to make that circumference, gives us the velocity, because it gives us how much time we traveled per second as an average velocity. And we don't even need to say average velocity, because the velocity is constant, meaning it is traveling the same rate. So this is uniformly split up into time. And in simple terms, since it's going the same rate as everything, we can just use one velocity term, because it's going the same speed as right here and right here. And the time it takes to do one lap, and if you divide the circumference by the time, it gives us how many meters per second. And again, that is velocity, because that is technically the slope formula. So we start at the initial point, and then the initial position we could set as 0, and then just a delta time. So same thing here, 2 pi r delta time, or how much time it takes to do one lap. And that gives us the amount of distance per second. I mean, I really don't know how much simpler it could get, but that's the logic there. So yeah.